What's up guys, and welcome to this video. We are doing question 2 of the 2016 final exam. Okay, so the question is on kinematics. Okay, so an experimental rocket designed to land upright was tested recently. During liftoff, the velocity time graph was recorded. I assume that's the graph below. Okay, so we start off with a definition. 2.1, define acceleration. Okay, so acceleration is the rate of change of velocity. Okay, and we get 2 marks for that. Cool stuff. Then it says calculate the acceleration of the rocket during the first stage, A to B. Okay, so remember when we've been given a velocity time graph, the acceleration is equal to our gradient. Okay, so we can say that the acceleration is equal to the gradient, which is equal to change in y over change in x. Okay, let's take B as 0.2 and A as 0.1. Okay, so our change in y is going to be 230,4 minus 0 over our change in x is going to be 120 minus 0. So our acceleration is equal to 1,92 meters per second squared. Okay, and acceleration is a vector, so we need to give a direction. The gradient is positive, and this is for liftoff, so we can say that it is upwards or up. Okay, and that's the final answer, and we get 4 marks for that. Okay, so it says the rockets are then fired second stage, B to C, before turning off at 270. Okay, so the rockets are then fired between B and C before they turned off at 270. Okay, so here rockets are off. Cool stuff. So describe the velocity and acceleration from C to D. Direction must be included. Okay, so let's start off by looking at the velocity. Okay, so so as we can see, the velocity goes from 270 to 0. Okay, so we can say the velocity is slowing down, or we can say a better way to say this is the velocity, okay, is up. So it's still moving upwards. Remember, it's still moving upwards. Although the gradient is negative, the area, which is our displacement, is positive. Okay, so we have a positive area, so it's still moving upwards, so the velocity must still be upwards. So velocity is up and decreasing in magnitude. Okay, does that make sense? So we are decreasing in magnitude. We're going from 270 and we're ending up at 0, the velocity. Okay, and then the acceleration. Okay, so the direction of the acceleration here, we have a negative gradient, so acceleration must be downwards. Okay, so acceleration is down. Okay, and we've got a constant acceleration, right? Because we have a slope, a flat straight line slope. Okay, so we can say, and the magnitude and the okay, so we can say acceleration is down and constant in magnitude. Okay, so I hope that makes sense. So our velocity is positive, so it's up, but it's decreasing. Whereas our acceleration, we have a constant gradient here, so it's constant, but the gradient is negative, so it is accelerating downwards. Okay, so it's slowing down. Okay, and we get 4 marks for that. At what time did the rocket reach its maximum height of that value? Okay, so remember, when we're talking about displacement, we're looking at the areas. Here, this is a positive area, this is a positive area, and this is a positive area, so the maximum would be at the final time. So 2.4 at t equals 297,64 seconds. Okay, don't forget your units. Okay, and we get 2 marks for that. Okay, just as a different scenario, if this graph went, let's say, stopped here and went like this into the negative part, the maximum height would have been wherever this time is. Okay, because when the area becomes negative, it means it's now moving downwards. Okay, cool stuff. And we move on to 2.5. Okay, we've got a definition. Before I even read the question, I'm just going to put down the definition. Define speed. Okay, so what is speed? Speed is, let's just say, speed is the rate of change of distance. Okay, and we get 2 marks of that. Okay, let's read the question. The rocket then fell freely from the height of that much, from rest, so u, initial velocity, equals 0. The displacement s is equal to 5, okay, that value there, I'm not going to rewrite it. Okay, at a height of 6,000 meters, the rocket engines fire and provide a constant acceleration until it reaches the ground with a speed of 1 meter per second. Okay, cool stuff. So question 2.6. Okay, so what we have is, let's draw out the scenario. Where can I draw it out? Let's see if I can. Let's draw it out in the top here. Okay, so what's happening here? Let's actually draw it here. Okay, so the scenario here is we have the rocket at 5,000 whatever height. It starts to fall down, and then the rockets fire again, and it falls down at a constant acceleration, at a different constant acceleration. Okay, so acceleration here, acceleration 1, and this is acceleration 2, and acceleration 1 is not equal to acceleration 2. Okay, cool stuff. Now that we have that covered, let's see, calculate the magnitude of the rocket's calculate the magnitude of the rocket's velocity at a height of 6,000 meters. Okay, cool stuff. So we're gonna have to start off. Remember this for the first part of this, it's in free fall, right? So we can use our UVATs, UVATS. Okay, so I'm going to take downwards as positive. That just makes our life a little bit easier. So the initial is 0. The final is the unknown, which we're looking for. The acceleration is 9,8. Positive 9,8 because I've taken down as positive. Time is unknown as well. And the displacement. Okay, is the displacement 55165,34? No, because it says at a height of 6,000. So it's that height minus 6,000. Okay. Okay, with that being said, we can use an equation. Let's use the equation v squared equals u squared plus 2as. So we have v squared is, or let's say v is equal to u squared, so 0 squared plus 2 times 9,8 times 55165,34 minus 6,000. Okay, and all of that is square rooted. Okay, the only unknown here is v, so we can solve for v, and v is equal to 981,65 meters per second. It says magnitude, so we don't care about the direction. If we did, this came out positive, so it would be down. Okay, but we don't care about that, so let's take that out actually. Cool stuff. Okay, question 2.7. Calculate the magnitude of the rocket's acceleration during the last 6,000 meters. Okay, so calculate the acceleration. So we care about the acceleration for the last 6,000 meters. Okay, so 2.7, I'll do up here. Again, we're going to have to use UVATs, UVATS. Okay, so remember the final answer for the last question is going to be our initial velocity now. Okay, so U is going to be 981,65. Okay, and again, I'm taking down as positive. G is going to be an unknown, or acceleration is unknown. The final velocity reaches a ground speed at 1 meter per second. So the final velocity is going to be 1. The time is unknown, and the displacement is 6,000. Okay, what are we going to use? Same equation. That's kind of boring, but v squared equals u squared plus 2as. So we're left with 1 squared is equal to 981,65 squared plus 2 times an acceleration, which is unknown, times a displacement of 6,000 downwards, which is why it's positive. Okay, let's see. We have one unknown, which is the acceleration. So if we solve for the acceleration, we get acceleration is equal to minus 80,3 meters per second squared. Okay, what does this minus indicate? This is simply a direction. Okay, so we took down as being positive in this part, so it's going to be acceleration equals 80,3 meters per second squared up. Okay, but this answer is sufficient because it says magnitude. We don't care about the direction. Okay, cool stuff. So the next question says the rocket has a mass equals 5,800 kilograms. Good to know. Question 2.8. Draw a labeled free body diagram of the rocket during the last 6,000 meters. The relative sizes of the forces must be clear. Okay, so remember, it's traveling at 6,000 meters, it's traveling at 981 meters per second. At the end, it's traveling at 1 meter per second. Okay, so obviously the thrust has to be very big compared to the weight to slow it down. Okay, so the relative sizes just mean draw the arrows accordingly. So we're going to call this thrust. Okay, and I'm going to draw the weight much smaller than the thrust. Okay, basically we can even put in there, just to make it more clear, that thrust is greater than weight. Okay, and we get 2 marks for that. Okay, question 2.9. Calculate the thrust exerted on the rocket during the last 6,000 meters. Okay, so we're talking about forces here. Okay, so I'm going to say that F net is equal to MA, and I am going to take what direction as being positive? Let's take upwards as being positive. So we're taking upwards as being positive. Okay, so the net forces is going to be thrust minus weight is equal to mass times acceleration. Okay, so we have thrust is equal to mass times acceleration plus weight, which is mg. So we can say that thrust is equal to mass times a plus g. So we have thrust is equal to the mass of the rocket, which was 5,800. Acceleration we calculated before as 80,3, and gravity, which we know is 9,8. Okay, so we can calculate from this, we can get the thrust, and T, or thrust, is equal to, okay, so thrust is equal to 522,599,17 newtons. Okay, so we need to give a direction. So the answer came out positive, and we chose upwards as positive, so the thrust must be upwards, and that makes sense, right? Sometimes it's important to ask ourselves, does this make sense? If we came out with a negative answer, right? If we came out with a negative answer, we know we've made a mistake somewhere. Okay, and sometimes even if you're running out of time and you know something's wrong, sometimes it's better to just put a note there, just saying that the direction came out negative, or the thrust came out negative, which you assume to be incorrect. Sometimes you can get marks for that because you show that you're understanding the work. Okay, so yeah, that's the end of that question. In the next question, we will continue. In the next video, we will continue at question 3. But we got 27 marks, which is really good, which is more than 10% of the paper, I think. And it only took us, let's see how long it took, roughly 15 minutes. Okay, so pretty good. Cool stuff, guys. Thanks for watching, and I hope you found it useful. Cheers.